everyone, my name is Leona Duncan, and for my CPE187 final, I built a miniature standing desk that showcases the embedded systems concepts that we've gone over, mechanics, electronics, and firmware. I'm going to be walking you through the system architecture, my component choices, the control logic, test results, and what I would improve in the future. So for team members and responsibilities, I was the only team member, that is me, and I was responsible for every part of this project. I handled the mechanical and electrical design, the breadboard wiring, all of the testing, all the debugging, buying all the components, the sensors, power, and writing all the firmware. I did everything. So a description of the project. The purpose here was to create a small and functional model of a standing desk powered by an STM32. So the desk features a push button for input. The desk changes height, and it displays the height at any given time to this OLED screen via a time-of-flight sensor that is underneath the board here. You can't see it, but it's actually pinned underneath this desktop. So my design goals were it needs to move, it needs to be stable and not fall apart, and it needs to give accurate height measurement and report that to the OLED so the user can actually see what the height is at any given time. Just like a normal standing desk, I just need it to move and tell me where it is. So here is my block diagram. I used two MCUs. I used the L432KC and the F303K8. One thing here, I actually have these two things switched. The F303K8 was here, and the L432KC was here. But other than that, this is correct. I originally was going to use two L432KCs, but I was going to have two, and then have them both handle two different things, and at the end combine them onto one. But I actually broke one of them on accident by dropping it, so I put in an F303K8 just so I could debug them separately, and I left them separate just for the purpose of being able to demo something that I knew that worked. I didn't want to complicate it by mixing it up at the very end right before it was due. So let's go through these real quick, keeping in mind that these are actually switched. So we have a input GPIO push button that sends an input information to the board. This board is powered by a USB, and this information goes through to the step and direction, which is being sent to the motor driver. The motor driver is also powered separately by this 12-volt power adapter. So it's not actually being powered to turn on by this. It handles this power and sends it to the motor because the motor requires 12 volts to operate. So don't mix these two up, because if you send 5 volts to here, this is not going to be able to work because it's not enough voltage. And if you send 12 volts to this, it's going to fry it. So this goes through. We have the coils being attached to the motor driver. I will show that later so we can see what this actually means. And that is connected to a coupler, which is just connecting to the shaft of the stepper motor to the screw in the desktop, which is how we get linear movement. So for the other board, also powered by USB, and that goes has I2C daisy chaining between the OLED display and the time-of-flight sensor, because they're both communicating through I2C, but they have different addresses, so we can daisy chain them together and they won't compete with each other to work. They'll work fine. So I'm just going to quickly get into the components that I use for this assignment. So let's go over the lead screw, brass nut, and coupler, and I'm also going to go over the stepper motor right now because they make sense to talk about together. The screw and the nut are basically converting rotational movement of the stepper motor to vertical movement or linear movement. So this is spinning, and when it spins, it goes up or down the screw depending on which way we're spinning it. And that is linear movement. If you have it straight upward, that's it going up or down, or if you have it horizontal going left or right. So this is just taking a rotational movement and converting it into a linear movement, up, down, left, right. This coupler is just to connect this screw to this motor. So this goes like right here, and it connects the screw to the motor. The stepper motor, this is an EMA 17 stepper motor. This is what provides the rotation to the screw. Otherwise, how is this moving? So this is what spins it. And you just connect this on top, the screw on top of there, and this will spin it in whatever direction you specify that we want to be spinning it, which will cause the nut to go up or down, or left or right if you have this on its side. These are ball bearings. Ball bearings are just a load-bearing mechanism, which is intended to support and lessen the load on something. So an issue that I was having here that I will go in more in depth later was the axial load. So when we have a motor like this, if load is coming directly downward towards this shaft, that is called axial load. And what happens is when you have too much load pushing down on the shaft, it's pushing down on the mechanism in here, and it can't spin anymore. It's like pushing too hard down on it. So these bearings are meant to lessen the axial load, which ensures that the motor will not stall and will get pushed down too hard to where it can't spin anymore when the input is being put in. Moving onward, we have the stepper motor driver, which is a TMC2209. This controls the current microstepping and direction of the stepper motor. So basically, this is protecting the motor, and this lets us set the torque. It is allowing for smooth movement. The step and direction interface allows us to toggle the step frequency in which we want to do and the direction of which we were going, in this case, up or down. And when we were wiring this all together, the only things we used here were VDD, which is the power. This is the power for this device, for this board, sent by the microcontroller. Ground from the microcontroller, direction and step are both connected to the microcontroller because we're going to need that information. And then enable. The rest of these pins were not used. We didn't need them. And then up here, this is what actually connects to the motor. I'll show a picture of it later to show the actual wiring. But so we have here, this is the power, the plus and negative rails for the power for the motor. This is where the 12 volts plugs in, is right here. This down here is going to be the 3v3. And then otherwise, these are the coils. So we have 1 and 2A, and then 1 and 2B. Basically, the motor has coils in it, coils 1 and 2. You just want to make sure that coil 1, which has 2 wires, is on the A's and coil 2 is on the B's, or vice versa, but don't mix them up or else it's not going to work. For the display, we have an OLED display. This is the same display that we used for the OLED display lab in class if you decided to do that lab. And this is just communicating via I2C. We have a STEMA connector here for easy connection, but you could also solder up here. And this allows us to see the current desk height. Additionally, this is the time of flight sensor. Basically how this works is it sends a pulse of infrared light out that hits something and then bounces back. And it is taking the measurement of time for how long it was sent out and then came back, divide that by 2, and we have the distance. And this also communicates via I2C. It also has the STEMA QT connectors. So we were actually able to daisy chain these two together via a connection like this instead of having to use the soldered pins. So finally, we have the 12-volt power adapter. This is for the motor, as we said before. It just provides a stable voltage to that goes through the stepper driver and then powers the motor. This is a female adapter that goes on the edge of this because I can't plug this in directly to the board at any point. So this goes onto here, and then I can put two little wires in here, a negative black wire and a red wire here, and plug that into the motor driver so that I can supply the power in there. And then finally, we have these STEMA QT cables, which I talked about a little bit before. They're not necessary. You can directly wire this on your breadboard, but they are convenient because they allow me to connect things easily and not have to worry about extra soldering. So I only had to solder the motor driver board. So I'm going to be going over the firmware for the assignment. As I said before, that I used two different MCUs, so we're going to see two different MCU IOC layouts here. The logic for the assignment was written in C using STM32 IDE and HAL libraries. So for the top one, the L432KC, we can see the I2C because this is the board that was controlling both the OLED and the time of flight sensor. For the bottom one, this is going to be controlling the motor driver and processing the button input. So we have the step direction and enable here, and then we have the button input right here. I'm just going to be going over some of the code here. So for the top block here, we have some helper drivers. For the driver being enabled, low is the driver enabled and high is the driver disabled. And then for the driver direction, 1 is going to be down, which is high, and then 0 is going to be up, which is low. I don't show up here because up did not work in my testing. So this is just me going over the logic for the down. If the button is pressed for down, then the driver direction needs to be down. We have a stepper rate of 4,000 kilohertz, which is just for the speed. You can change this. It'll make it go faster or slower depending on the value you put in here. And we're going to enable the driver and turn it on. Otherwise, if the button is not pressed, then the stepper rate is going to be 0. We don't want it to be moving, and the driver is going to be disabled. So in the bottom left, we have the offset. Basically, the sensor is attached to a breadboard on the bottom of the desktop, and that has some thickness. So to get the actual height that I need for the desktop height measurement, I need to take into account that there is some thickness that we are losing and add that after the calibration to get the desk surface height. So on the right here, we have the L53 read millimeter single shot ranging, and on the STM website they have a lot of resources for the VL53 type boards because the sensor is a pretty universal sensor for time of flight. So this is pulled from that, and also from there was a Arduino library in GitHub that had this type of logic, but more so in Python, and taking those two and kind of mushing them together. But basically what this does is it clears previous interrupts and starts a single shot measurement and then pulls, and then on success it'll read the result range millimeter into millimeter and then clear the interrupt again. So this top block here is just going to be setting up the OLED, we having it, filling in the screen, setting up the cursor, setting up the labeling, and getting ready to start posting the measurements that we're getting from the sensor. This is where we're actually taking the information and we're reading it. We're taking that information, we're applying the calibration, we're taking that corrected value, and we're applying the offset, which is the 19.05 millimeters we were talking about earlier. This is adding that to the measurement that we took and to get the true measurement. And then we're going to take that measurement and we're going to convert it to inches. We're going to post both these measurements onto the screen. So this is setting up the screen. This is taking all those measurements and actually posting it to the screen. And this is happening over and over and over and over again. So it's constantly repopulating the screen with the new information. On the right here, we have the UART debug. This is just before I had the OLED screen working, to be able to see this output and see that the sensor's working, seeing that the calculation's working, and being able to post that all to a serial terminal so I can see all the values constantly getting populated there. So as far as related course topics that we went over, we use GPIO configuration for the buttons and driver pins. So that is just this button here is GPIO input. It's going up to this pin here. We got an internal resistor set up, so I don't have to have a physical external resistor. So just basically like stuff like wiring on the breadboard is this configuration. For the timers and pulse width modulation, we used it for step pulse timing for the smooth movement of the motor. We used I2C communication for both the OLED and the sensor. I don't have the OLED picture here. It's on the other side of this desk, but this is the sensor. So here we see the STEMA QT cables again coming around for the I2C communication. We used debouncing for reliable input for the button so that it knows when we're actually pressing it and it's not getting too noisy. And we used power considerations to make sure that we're using the right power for the right thing. So again, I talked about earlier, but I'll talk about it again. We have 3v3 here. It's coming through here to the power rail, coming back out, and up here to VDD, powering this module, but not powering the motor. The motor is being powered by this. This is the this is from the 12-volt power adapter. So this is going sent here through, and this goes to the motor. So don't mix these up because it will not work and you will break your stuff. So I'm going to get into my test cases and talk about my successes and my failures. We said earlier that we want the standing desk to move, and it kind of moves. So what I mean by that is the down button. When I press the down button, the nut on the screw does move down. But when I press the up button, it does not move up. What happens is when I press the up button, it would try to go up, but then the nut would start slipping due to the vibration that's happening in the screw, and it would start slipping back down. So you'd have this nut that's trying to go up, and it's sliding back down, and it's going up, and it's sliding back down, and it's not really going anywhere. Down works because gravity is helping, but up was not working. So I lost the up functionality of my standing desk. Whenever I wanted to move it up, I'd have to manually spin the nut up the screw, kind of like if you had to manually crank your desk up, which is a failure because that is not what I was going for. The time of flight sensor does work. It does detect the desk height in millimeters. The OLED screen does work. It does display the output heights. My conversion works. The height is converted from millimeters to inches. Now the load handling, that was what we were talking about with the ball bearings earlier. when force is applied to the nut no longer spins on the screw because the axial load is too much and it's pushing down on the actual motor. All of the force down the screw is going all the way down and it's pushing on the motor. That friction is causing binding and the screw no longer is rotating. The load bearing ball bearings, those were supposed to take some of the load off of the screw and deposit it into those balls, so when it spins, some of it's getting dissipated there. That would work if my ball bearings fit the screw, but unfortunately I bought 2 different sizes of ball bearings and they were both just a little bit too small to fit the screw. So I wasn't actually able to apply them to my project. So yeah, if I want to move the desk down, and I'll show it in the demo, I kind of have to hold the weight of the desktop a little bit so that it's not too much weight on the motor, which is a failure. So overall results for the assignment, the motor driver does correctly communicate with the motor. My sensor is capable and does work to read the live desk height. The height is reported to the OLED screen and it is converted into inches, showing both of those different heights so that we can see that a more reasonable measurement of the height, because 206 millimeters might not mean much to you, but 8.1 inches is pretty easy to conceptualize. And it does actually accurately show the height. I did have a little bit of offset to take into account how much space there is underneath the desk, so it adds that height onto it. So that all works. But as we said before, upward motion doesn't work, and it does have issues with bearing the load of the actual desk. For future improvements and things that I'd want to change if I had more time, I'd like to consolidate all of this logic and all of these mechanics into one microcontroller. Because it is a bit cumbersome to have two, and because of having two, I decided not to implement presets because it would take considerably longer. If it's all on one board, having presets is not too bad because the logic of the height and the logic of the motor are on the same thing and they can communicate with each other easily. To do it on 2 boards, I'd have to send that data over something like UART to be like, hey, this board's telling the other board, this is what the height we want is. Now tell that information to the motor so we can get it there. That is kind of a lot, and I didn't want to have to deal with that. So if I had it on one board, that'd be a lot easier. I'd like to have upward movement. I'd like to try to get a bearing set up to where I can have this desk not be too cumbersome on the load of the motor, and I'd like the desk to be able to go up because that is what a desk used to do. So overall, the desk has some functionality of changing height. It can go down, and all of the measurement stuff is right, and the components work, but the components implemented with the actual frame of the desk have issues.